get started lecturing today. A couple things I want to mention is in grade scope, or not grade scope, what is this? This is Canvas, right? I set this up, I'm pretty proud of myself. I got it all, everything working. One thing to note, if you do the grade scope, right, I imported all of you guys into grade scope through Canvas, and so it's using whatever email it does when it does that converting. I'm not going to give you a code to sign up for things because then we get some weird stuff. If for some reason you go to Gradescope or go to this link and it's not showing up, it might be because you use a different email address when you sign into this. And then there's a mechanism for merging those emails, the one that they're using for Canvas and the one that you're used to using. And I put the instructions for that in here. The other thing to note is if you try to access through an iPad or a Mac, it does not work with Safari. This link internal to Canvas. You can still go to gradescope.com or whatever and log in that way, and it'll work just fine on your iPad. But when you try to do the link through Canvas, that doesn't work. You just get a blank screen like I'm getting right here. Okay. And if you're still having trouble, logging in and it's not the email, whatever it is, just reach out and we'll try to figure something out. I also provided some instructions in here somewhere. And then under assignments, you'll see that's where I'm gonna have all of your assignments posted. The only thing I have posted right now is homework 1. And then I have the midterms in here just so you can see the dates, right? And I do that. Homework 1, you can see I have assigned at this point, right? And so there's a little description. That's how I'm gonna do it. I'm not gonna give you a handout. I'm just gonna do it through here. So a little description of what your homework problems are, right? These are right out of the book, right? You could probably track down a solutions manual for these, right? You gotta be careful with that, right? Historically, if you rely on that too much, the solutions manual, then it's not gonna work out for you, right? When we do an exam, I'll find you that you've been, copying the solutions. But if you use it right, it's just like a peek every once in a while, not really diving in too much, okay? Not relying on it too much. Starting next week, Anika will be in the Learning Center to help with these homeworks. And a very common thing that people have done if you didn't use this for statics is you could just go work on your homework in the Learning Center when she's around and she's there to help you. She has all the solutions. She knows how to do all the problems. She took this class from me a couple years ago. And so gotta get ready for that. And so underneath homework 1, I do put some directions on how to use Gradescope if you haven't done so already. Any questions about this? Just some logistics. Good. Cool. All right. Side note 2, if you get here early on Fridays, one of the janitors brings donuts. So if you get here early enough, you get free donut. And it's Granny's Donuts. So who all benefited from that? I literally, no joke, get up about 15 minutes earlier on Fridays just so I could come and get a free donut. Because if you wait till right before class, you're not going to get one. I'm the type of guy that really likes free donuts. Okay. So let's dive in, right? So I posted all these. These are under Canvas as well, right? Everybody track these down. There's PDFs of the skeleton notes, right? So I'm just going to start out with this and just fill these suckers in as we go along, right? One thing you'll notice pretty quickly, I have terrible handwriting. I apologize. But I think you're going to be okay. I type where I need to type, yeah.
As the images aren't on the
Yeah, I know. I added those last night, so you can quickly sketch them. Yeah. And sometimes I'll do that. Most of the time I stick with it. I've used the same set of notes for quite some time, but then last night I was like, oh, wouldn't a visual be nice? And so I threw these graphics in there. You'll see the handwriting isn't the best, but like when it's really critical, I'll type it just so you can read it. Okay. And the other thing is, like, even though my handwriting's not nice, I still make my solutions really clean and tight and easy to follow. So that's something you can strive for. I used to be really embarrassed about my handwriting, but then now I see all your guys' handwriting. There's some of you who are really good, but then I see yours too. And it's like you can't be throwing stones unless you're have beautiful handwriting. If you have beautiful handwriting, go ahead, you can throw stones at me. But it's also really unfortunate is, and those of you that have bad handwriting, the harder I concentrate on not having bad handwriting, my handwriting becomes worse, right? And you'll understand that. Right? And then also, my handwriting is worse when I try talking while I'm writing. I'm in like the one profession in the world where you have to talk and write at the same time. This is unfortunate circumstances. Okay, so statics. Just this introduction to dynamics to get things started, right? In statics, we talked about this last time, or at least mentioned it, right? some of the forces were equal to 0, and some of the moments were equal to 0. Right? That was a key concept. I mean, that was the concept in statics, right? It was all about getting some of the forces equal to 0 and some of the moments being equal to 0. We drew free body diagrams. We looked at all this stuff. We summed all the forces. We summed all the moments. We knew they had to be equal to 0 because they weren't moving, and so then out popped some unknown variables, right? In dynamics, though, we're going to complicate things. Sum of the forces is equal to mass times acceleration, right? The line above there, I'm going to try to be pretty consistent with it. The lines above the variables denote that it's a vector. Right? I don't know. I'm sure you did that in statics as well. I'll try to stick to that as best I can throughout. But if you see the line over, that means that it's a vector. Okay. Some of the forces equal to mass times acceleration. Some of the moments, though, right? I'd like to be able to say some nice clean value, but it's not clean. So we're just going to say that some of the moments do not equal 0. Right, that's what we're gonna get. That's all we're gonna say here. The other thing about it, right, is some of the moments not equal to 0. When we get to 3D rigid body dynamics, the sum of the moments are gonna be the biggest equations you've ever seen. They're Euler moment equations is what they are, and they're massive. Right? Honestly, I want to say it's probably the longest equation you've ever seen. Cool. You're gonna look forward to that, right? You're gonna look forward to that. Let me do one thing. I wanted to point one more thing out. I forgot one more motivation for you. Kind of related to this. I know, we'll get to there in a second. Okay, we'll do it. Yep, okay. I'm going to come back to that. Okay, so this would be one of those cases where we're going to write a little bit, so I'm going to type. The structure of the course. How are we handling this course? Okay. What we're going to do, the first thing we're going to do is we're going to start out with particles. Right? Mass is concentrated at a point. Right? And all of you have taken physics 1, maybe even high school, right? And you did, right, projectile motion problems in physics in high school, right? And, or even here. You guys all took physics here as well, right? Here, unless you did an AP out of physics. Anyways, you've done it. And you've done it, like, oh my gosh. And so a lot of this right at the beginning is gonna seem like review. Like, why am I doing this again? That is just the very first little fraction of this class. Immediately we take away from, we almost immediately, we start branching away from what you did in physics. Right? Physics, everything was a function of time. We're going to have things as a function of position and functions of velocity and things like that. Okay, so particles, mass, and concentration, similar to physics, okay? That'll be, and then there'll be a test, right, after that. Right? Then we're going to go to 2D rigid bodies. Right? In this type of problem, our mass is distributed. Distributed mass. Right? Body is non-deformable. That's what the rigid part means. Right? Particles, just a little concentrated mass. That's why I added these graphics. Let's take a second to look at these graphics. These here, the top one here is particles. Right? This is the type of problem we're going to have. Your projectile motion problem, right? Here's a golfer. The golfer's shooting the ball, and right, the ball is going to be modeled. We're going to, in our mathematical model, it's just going to be a point, right? And we're tracking that point as it flies through there. That's particles, okay? Then we're going to do 2D rigid bodies, right? Right here, you know, our masses are concentrated at a point. It's just located at one location. Rigid bodies, right? Well, I have to take into consideration that this thing's mass is not concentrated at a point. It is distributed along its length, right? And so that would be a 2D rigid body. And the reason we add in the rigid body part and call it out as being rigid body is because we're not going to take into consideration that while this thing is moving, these things will actually be bending, right? They'll bend and they'll deflect and stuff like that. That's what you're going to be learning in mechanics and materials, is how does this thing deform under forces, right? But in dynamics, we treat them completely separate. But in reality, it will be deforming and it'll be moving at the same time. That is a graduate level class when you have to deal with both of those things happening. But for here, we're just going to keep them separated, right? In mechanics and materials, you're going to be looking at how these things are bending under a static case. Dynamics, we'll look at as if they're moving, but we're not going to take into consideration that are also deforming. okay? That's why that is. So then that's going to be the 2D rigid bodies, okay? That's the second part of the class. Then there'll be an exam, okay? And the third thing we're going to do is 3D rigid bodies. I hate typing on an iPad, but it works that way. Okay, that's kind of the main structure. And I'm going to talk about what we're going to do under each one of these things here. So 3D rigid bodies is the last case down here. This guy right here. Okay, you got this object that has a distributed mass. That's what this is. This object has a distributed mass. It's rotating about an axis, and that axis is also rotating. And some really weird stuff happens when you have this going down. Like really weird stuff that happens when you have these things going down. And that's why we end up with these really big moment equations that I mentioned before. Let me show you what the last problem we're going to do. Hold on, give me 1 second. I'm going to track down this example. I usually bring a visual aid with me, but I just have a video today. You know, you guys may have done this or messed around with this in physics class. I have this wheel. It's in my office. I forgot to bring it today. Also, I don't like to carry it across campus because it gives me away as not being a student when I'm carrying a wheel across campus. So I don't want to give that away. All right. So this is just a standard wheel, right? And then this is by a former TA of ours, Trig, and he's holding it by a string. And that string isn't centered on the axis; it's off center, right? And so when Trig, my wonderful assistant, is going to show me or show us something cool. All right. Hang by one, and it doesn't fall down, and it hangs there. Okay, that was it. I mean, so it's really cool when you see it in person. I think it's really cool because you'd think, right, your static mind would be, all right, well, when he lets go of that thing, since I'm holding it off center and I let go of it, it's just gonna fall over, right? I mean, that's my statics mind. That's actually how my mind will always think, is it's gonna fall. Even though I've taught this class 10 times, I still think like, man, it should fall. And then it doesn't fall. I'm like, oh my God, it's magic, right? I would not recommend going back in time. Don't show this to people because then they might think that you're like some sort of witch, and then you get burned to the stake or something, right? Because you're doing some weird stuff. Didn't that happen like the original? It's going back too far. The original Planet of the Apes. He like made a paper airplane and threw a paper airplane. They're like, whoa! No, nobody see that. Anyways, don't do that. And so this is the very last problem. It wasn't spinning. Show them what happened if it wasn't spinning. Let me stop it. Yeah, it does that, right? That's weird. And you all experienced a little bit, right? Why when you're riding your bike, as long as you're moving, you're stationary. But as soon as you try to stop and hold it in one place, then you fall over because you're missing that stability that's provided by the wheel turning. But the very last problem we're going to do in this class is that problem. Okay, then we're gonna have a wheel spinning, and we'll be able to figure out when you let go of it, it's gonna say it's not falling down. And what it does instead is it processes, is what it's called, right? So when you let go of it, it didn't just stay put, it started processing around an axis. So the very last problem we're gonna do is that. And it's a long journey. It's 15 weeks to get to a point where we can explain mathematically what's happening there. Physically what's happening, like can I explain? No, I kind of can. I kind of have an intuition now, and I'll try to explain to you when we get there of like why the thing doesn't fall down. But mathematically, we're gonna trust our math, and we're gonna do cross products and all sorts of stuff, and then our math is gonna say it's not gonna fall down, it's gonna rotate around, and then we'll be able to trust that. But intuitively is what I'm trying to say. It's not easy. It's not easy. And so that's another thing I'm going to stress in here is when we get later on, when we're doing these 2D rigid bodies and 3D rigid bodies, we are not going to trust our intuition. You don't have an intuition for this, right? You don't, because where you get intuition is from dealing with these problems a lot. And then you're going to try to take some of your concepts that you had from high school physics and apply it to something, and they're not going to work because there's too much shit going on. There's too much stuff. But the math is going to help us through all of that. Okay. All right. So under each one of these, so that's what we're gonna do. Particles, rigid bodies, 3Ds, right? That's what we're gonna do. Under each one of those things, we have three things we're gonna do. First thing we're gonna study is kinematics. Okay, which is the geometry of motion. Right? In this case, there's no forces. When we're talking about kinematics, there's no forces. Then the next thing we're going to move on to is kinetics. These are forces resulting in motion. So we're going to start out just kinematics. We're just going to look at the geometry of motion. We're not going to say anything about forces. Then once we get that down, we're like, yep, we got it, we understand it. Then we're gonna go down to kinetics, and we're gonna do forces resulting in motion. So that's where we're gonna start doing free body diagrams and tying forces to accelerations. Okay. Then the last thing we're gonna do, I guess under kinetics, there's three different things we're gonna do. One of the things we're gonna do is FMA. Right? These are force, mass, acceleration. Right. These are going to be F equals ma. Right. So we're going to deal with these problems where our force is equal to mass times acceleration. Right. We're going to use that equation. That's Newton's second law, right? We're just going to use that equation to solve these problems. But then we're also going to, some problems are going to be easier to solve with work energy. Right? There's certain types of problems that just scream, use work energy to solve these problems, right? And the last one we're going to do is impulse momentum. Three different ways of solving these problems. Right? And we're going to use this for collisions. Because the energy is not conserved in a collision, okay? So each one of those, I like to kind of go over what it is, where we're headed. So we're going to do that for each one. So we're going to start out with particles, then we're going to do kinematics, just forces, geometry of motion without any forces. Then under particles, we're going to do kinetics. We're going to do force, mass, acceleration. We're going to draw some free body diagrams that set force is equal to mass times acceleration. Then we're going to do, for particles, work energy. And then for particles, we'll do impulse momentum, take an exam. Then we'll do 2D rigid bodies, kinematics, just the geometry of motion. Then F equals ma, then work energy, then impulse momentum, take an exam. And then 3D, we'll do kinematics, geometry of motion, kinetics, F equals ma, and then we're done. Okay, we're not going to do work energy or impulse momentum for the 3D stuff. It's complicated enough on its own, and we'll just kind of do that right at the end, right around Christmas. Right around Christmas, we'll be doing that stuff at the end. Quick little rush at the end. Any questions about that so far? Okay. We get a little excited. I really enjoy this class because trying to explain this, we get to explain how that wheel that we just saw, how that works. It's pretty cool. Again, coming from a world where we set up our problems to just say, sit, stay, don't ever move, right? That's where I'm coming from. And now I'm in this, I get to play around in this world where things flying around, okay? We'll get a little philosophical on occasions. All right, so like I said, we're gonna start out with particles, right? So for the next, till, that's 5 weeks or so, we're gonna be dealing with particles. Right, and then once we get done with that, so again, this is going to look like review, and it is going to be review for probably the first couple of days, and then after that, it's going to be some new stuff. I'm going to argue this. I don't know if anybody would agree with me. I think the stuff here at the beginning, doing these particles, is harder than the stuff later on in the semester. I really do. This one is you got a little ad hoc. I'm going to try to put some structure on how to solve them. This is the procedure that you're going to use, but some of it's just ooh, you gotta kind of think, should I try this way? Should I try that way? I don't know. Should I do it this? Should I do it that? Should I integrate like this or not? Right? There's that. When we get onto the later stuff, I'm going to give you a procedure. It's going to say, do this. Start here, work your way this way, follow this rigid procedure, do the same thing, work your way around from this. It's very structured. The stuff at the beginning, I think, is a little bit more difficult. You'll see. Just the first couple of homeworks. And then once you get past that, smooth sailing. That being said, I say that I say that, but historically the grades start out here and then they go down. So just to the very first part, you want to set yourself up high so that as the semester goes on and you're dipping, you still make it through. Okay. That instill lots of confidence in you. Okay, so this is gonna be a particle, right? So we just gotta define some basic stuff here. So there's a particle here, that's this black dot, and then here it is a short time later, right? And it's traveling along that path. So it's going from one point to another point, okay? And we're gonna just briefly define some key components. First thing we're gonna do is define position, right? So my position, right, it's gonna be relative to something, right? It's gonna be relative to an origin of the coordinate system, okay? And so my coordinate system, it can be anywhere, right? In this case, I just have it down here, right? And so it has a position relative to that origin, right? And we're gonna define that with a vector, okay? So we got a vector that's pointed at that point to begin with, right? And that position we call R, for all the R's in the word position. It's one of my favorite jokes. I will use it throughout the whole semester. I don't care if you think it's funny or not, I'll still use it. Because they do this a lot in this class. Because I'm gonna use what they do in the book, right? I'm gonna use the same nomenclature they use in the book. In the book, they call position R, okay? And then it's funny just to say, because there's no R's in the word position. See, does it get the joke? Yeah, there we go, yeah. There we go. Okay, right? And then a short time later, it's moved, right? So it's over here. Now its position is over here. Right? And so this is going to be the position R, but it's not of just the time, it's the time plus a delta t. Right? It's the position R at t plus delta t. Okay? And then we could define a vector that goes in between them. Okay? That vector right there is what we're going to call delta R. Right? Is how R has changed. Right? And how R has changed is going to be R of t plus delta t minus r of t. Just vector addition, if you remember that, right? That if I want to get to this point right here, I could just do r plus delta r, and then it'll get me to that point, right? By adding vectors and stuff. And so trying to figure out what delta r is, I just do r of t plus delta t minus r of t, and it'll tell me what that delta r is. Okay? Right, and again, that line there is the path that this particle is traveling on. Okay, so now I've got position defined, right? Let me define velocity, right? And velocity is defined, right, as the change in position over time, right? So my velocity equation, I'm trying to be very distinctive between my R's and V's here. My velocity as a function of time is equal to the limit as delta t approaches 0 of delta r over delta t. Right? I mean, again, this is just review, right? The change in position over the change in time. That'll tell us what my velocity is. And then it is a limit, right? Because right now, obviously, right, it's cutting that corner, right? But if I made my delta t really small, like over here someplace, right, then it's approaching the actual velocity, right? And so if my delta t goes to 0, then that's how I get my velocity, okay? And so another way to write this is in terms of derivatives, right? That's the definition of a derivative. So this is dr dt. That's literally the definition of what a derivative is. And this is what calculus was made for, right? Was to describe this. Right? To dr dt, that's the derivative. So the derivative of the position is equal to the velocity, right? This should be a vector over here. Right? And then another way to write that in shorthand is r dot. I'm gonna be a little carefuler with my is r dot. Right? And this may be the first time you see a dot over a variable. You ever see a dot over a variable? Right? That's a shorthand for I'm taking a derivative of it. Okay? I'm gonna put a little side note here just to get you prepped for a world of mechanics. Note, dot over variables, I'm going to zoom out here. Equals time derivative prime over variable denotes spatial derivative. It's kind of a fun little fact for you as you dive into mechanics a little bit more. Right? So mechanics of materials, right? You're going to be talking about, remember we're talking about deformed elements. When we talk about deformed elements, we're going to talk about derivatives with respect to x, right? How is my rotation changing with respect to x, or my displacement changing? You're going to get to this at some point, and you're going to use a shorthand in your equations, and they're going to be primes. And those primes denote, well, you're taking a derivative with respect to x or y or z or something like that. And here, though, when we take derivative with respect to time, you put a little dot on top of it. Does it have to be that way? No, but that's what it is in mechanics. That's what we call it, mechanics. Okay? Okay. All right, acceleration. Right, so we've defined, there's our velocity. Right? It's just it's just the derivative of the position with respect to time. Acceleration, similar idea here. Acceleration is a function of time. That's just going to be the derivative of the velocity with respect to time. How is the velocity changing with respect to time? Acceleration is a derivative of the velocity, which we can also write that as v dot. Okay? We can also call that r double dot. And since the velocity is r dot, its velocity is r dot, and acceleration is the derivative of the velocity. We could just call that r double dot. Okay, and we'll use this nomenclature quite a bit. Okay. And again, just review for you at this point. Okay. One other comment here: velocity. I just like to, again, I told you we're gonna be philosophical. Velocity is always tangent to the path. If not, you're not on the path. It's philosophical. I always like to give you something on a Friday to bring to a party on Friday night, right? And this is your first one for today, right? Did you know? Let's bring this up tonight. Did you know that velocity is always tangent to the path? But if you're not tangent to the path, that means you're not on the path, right? Deep shit right there, right? Yeah. Oh man, you're right. You're right. That is what's happening. Now you can see it here, right? Like I'd be on that pit. Like you're traveling along the path. Obviously, your velocity is along that path. If you're not in that, this is a concept that's worth pointing out. Okay. Here's another. It's some more deep thoughts for you today. Okay. Frame of reference and coordinate system. Right. This is what's this is a better one than the frame of reference or the thing I mentioned before. So say we have an airplane. Okay, I have an airplane and I'm standing on this airplane and I'm playing frisbee with my son. Right, so I'm right. Here I am, beautiful drawing, disc, throwing that to my son on this side over here, make him a little bit shorter. Even though he's taller than me now, but say maybe he's throwing the ball to me, they're throwing the frisbee to me, right? And I would say, well, how fast is that frisbee going, right? How fast is the frisbee going? Well, it depends, right? Like, what are we talking about? Like, what is our frame of reference, right? Am I down here, right? Right on the surface of the earth. I'm gonna draw the surface of the earth as being round, okay? We're gonna make that as an assumption. Later on, we're gonna pretend the Earth's flat, but like just want to make a point that it is in fact, I 100% believe it is a round planet. Okay, and we're looking up at it. So now, right? So how fast is that frisbee going? Well, what are we using as a frame of reference? Or is it this person down here on the surface of the Earth, and they're looking up and they're looking at it, and they're like, oh, Well, it's going, a certain speed. Is it what my son is doing? Is he's trying to catch the thing, right? So he's trying to catch it. It's 5 feet per second. I don't know how fast the frisbee goes, but it's just coming at him really slow. But how fast is it really going? Well, it's going really fast because the plane itself is traveling super fast, right? And so then, it'd be great to be able to say, oh, well, it'd be great if we could pick something that's actually not moving to be your frame of reference. Wouldn't that be great? So let's just pick the surface of the Earth. Fuck, right? That's moving, right? Theoretically. Theoretically, right? It's moving, right? Because it's rotating around the center of the Earth. So it's moving. Okay, well, let's pick the center of the Earth because that's not moving. Shit, it's moving too, if you believe in that thing. And then so we're traveling around the center of the sun. Well, let's assume the center of the sun's not moving. Shit, it's moving too, right? Because it's traveling around the center of the Milky Way galaxy, right? But then, okay, well, let's pick the center of the Milky Way. Nope, that shit's expanding, right? So what in the universe is not moving?
Nothing.
We don't fucking know. There's something out there that maybe isn't moving, but we don't know, and there is no way to know. Isn't that fucked up? That's some deep shit. That's a better one. That's a better Friday night conversation. It's like, there's no way to tell what is not moving. There's no, we can't pick it. There's nothing, right? It could be me, right? It could be, right? Everything else is moving relative to me in some capacity, right? Everything, right? But we don't know, and you can't tell. So anyways, this is some deep thoughts for you, right? So that's your frame of reference. What are we picking as the point that's not moving when we're talking about velocities and accelerations, right? We have to have some sort of frame of reference, right? So let's define that. Frame of reference. Right, we won't do that too crazy in here, right? It's the baseline. Right? Where we pick it is the baseline. What is something moving relative to? It has to be, when we define motion, we have to make it relative to something, okay? Typically, we assume it is not moving. In class, for our problems, typically the surface of the Earth. Right? That's typically what we're going to put as a frame of reference. Right? That's what we care about as engineers, right? Is that, and for all intents and purposes, this is not moving, right? It is, but relative to what we're going to be talking about, that's not moving, right? That's a frame of reference. There's a coordinate system. There's another thing that's floating around, right? A set of coordinates within a frame of reference. Right? Our favorite coordinate system, right, and its origin, right, we'll have some origins floating around, is we have Cartesian. That's our favorite, right? That's the XYZ coordinate system. Then we have polar. Right? That's probably a little less exciting, but then normal tangent is a new one. You haven't seen that one before, normal tangent. So we're going to deal with those three coordinate systems throughout here, right? But it's some place where I would set, all right, in this case, if I was talking about the center of the Earth not moving, I'd set my coordinate system, down here. Going to be, there's the origin, define the origin, and I'd start talking about the velocity of that frisbee relative to the surface of the Earth, right? And I'd set some sort of coordinate system for this. It's getting some basic definitions called out here. We'll take, what are we doing here? Oh, we got it. So this is another thing. I'm a huge fan of AI stuff. Which you may be as well. I don't know. It's really cool if you haven't played with it. I think by now everybody's played with it a little bit. One of my favorite things to do with AI is to give it language, and then, this I took directly out of the book describing what the frame of reference is, and then I put it into ChatGPT and I said, could you give this to me in Gen Z slang so that you guys can understand it? Are you Gen Zs?
Yes.
You are?
Yes.
You're not. The rest of you guys, everybody Gen Zs, right? So this is right? If you observe people in a room, such as a group or at a party, you perceive their positions relative to the room. For example, some people may be in the back of the room and some in the middle of the room and so forth. The room is your frame of reference. To make the idea precise, we can introduce Cartesian coordinate system, blah, blah, blah. Yo, peep this. If you're vibing at a party and you scope out the room, you'll clock where everyone's chilling. Like some peeps might be in the back, others in the center. You get the gist. Think of the room as your viewpoint. To get all technical, imagine we slap a grid on the room. It's pretty funny. And so one semester, I did every single announcement throughout the whole class. I translated it into Gen Z slang. I could do that again for you too if you want so you can understand. It actually does a really good job, right? It has not lost the meaning in what it was trying to say. It is process. Anyways, I just wanted to share that with you. That's how I sometimes I communicate with my kids. I have almost an 18-year-old and a 15-year-old, and I just jokingly every text I send them I translate it to Gen Z slang. Because again, trying to fit in. I'm trying to be one of you still, right? Okay, 1D motion. Let's kind of dive into this. So that's our first thing again, right? It's again still particles, and we're just gonna do 1D. And the reason we do this, right, is because it's simpler. There's no vectors to begin with, right? Because it's just 1D. We get to drop the vectors, right? What we learn for 1D, we carry on to 2D. Right? 2D is simply multiple 1D problems. So the book starts with this, and this is the reasons why. We don't have to deal with vectors, we're still getting going here, and then really 2D is just multiple 1D problems, right? You got 1D problem this way, 1D problem this way. You just treat them as separate and you solve them separately, okay? And so then, what they do is they say, well, my position vectors are, since it's just 1D, we get to drop the vectors. And for whatever reason, they call the position vector no longer R, they just call it S. S as not, and then no vector on it because it's just 1D. So for these problems, that's what they do. Okay? They call that S. Okay, and then just so in here, we're talking the velocity. The velocity is just going to be ds dt, which is equal to s dot, and acceleration is equal to dv dt, which is equal to v dot, which is equal to s double dot. Okay. Some other concepts that you may recall: if I have my plot of my position as a function of time, the velocity is the slope, because it's the derivative of it. So that's velocity in 1. And then if I have, same thing, if I have a plot of my velocity versus time, the slope of it is the acceleration. Right, rise of a run of those. And you remember that, right? You probably had plots of that before. That's just the definition of a derivative. The derivative is the slope of the line as you go along. Right. There's some basic stuff in this 1D things. Okay, now we get into starting to dive in here. Okay, so and this is me trying to put some structure to what's happening here. Throughout the text and throughout this section, you're gonna have 4 types of problems. Okay, we're gonna have accelerations a function of time, accelerations that are constant, accelerations that are a function of velocity, and accelerations that are a function of position. Okay, that's the 4 types of problems. And the way you solve these 4 problems are going to be different. This is what I'm saying. When you did physics before, I'm 99% sure all you did was acceleration as a function of time or acceleration as a constant. Probably even just accelerations that are constant, right? You didn't get into the two other types of problems that we have to solve. But that's going to be part of our way we're going to solve these things. We're going to say, all right, what type of problem? Acceleration function of time, constant, velocity, or position, right? And then you have to solve these ones different ways. Let's talk about these in a little more detail. When we talk about accelerations that are a function of time, any thoughts on cases, types of problems where acceleration would be a function of time? Look at it, something that's accelerating velocity. Yes, sir.
A car accelerating.
A car accelerating. That's perfect, right? That's a perfect example, right? In that situation, especially the old time and gas-powered engines that depend on RPMs, absolutely they're function of time, right? You step on that gas, the RPMs are low, it's not accelerating much, and then as the RPMs get up, it's accelerating faster. Switch it over to the next gear, same thing, you'll feel another boost, and then you do it again, you'll feel it again, right? It's changing as a function of time. That is the perfect example of acceleration. A car, a sprinter starting out, right? They start out accelerating not as fast as they get going more, then they accelerate more, or they stop accelerating as they go along because they've maxed out, right? Those are accelerations of time. Now, those are the types of problem you're used to. I don't want that. Accelerating car, sprinter, something like that. Okay? But accelerations that are constant acceleration. Yeah.
A ball dropping from a building.
Yes, but what's causing that?
Gravity.
Gravity, right? Is gravity constant? No, not. Right?
At a certain location.
Yeah, I mean, for all intents and purposes on the Earth, what we're going to treat it in this class is that gravity is constant until we get to orbital mechanics. That's the other thing we get to do at some point is we get to find what's going on orbital mechanics. Orbital mechanics, right? The further you go away, right? There's Newton's law of gravitation. It depends on the masses of the two objects and the distance that they're apart, right? And then that's how the gravity works there. But for here, we're going to say gravity problems, right? Gravity, G, right? G in this, we're gonna assume or pretend that it's constant. Okay, acceleration of function of velocity. Like I said, this might immediately be going to something you didn't do in physics. What would be something there? Think about forces. When are forces a function of velocity, right? Because remember, forces are related to accelerations. What's the case where forces are a function of velocity? Let's see, bro, is bro in here? Bro, do you have one? You're the only name I know. Or a guy. We got bro and guy, right? A bro or guy. You got thoughts? Okay? We'll go. Yeah, what you got? No, kind of. Eventually, yeah. We got someone else had it. Yeah.
Air resistance?
Yeah, there we go. Yeah. Same thing. Drag, right? Air resistance, right? Absolutely. The faster you go, the more force you feel back, right? The slower you go, the less force you get back, right? Any kind of fluid motion, right, is that way as well, right? And that is, and we'll just call that drag or air resistance, right? Right, or even viscous flow. Right, that's how a shock absorber works, right? In your car, right? If the load comes down, if you ever get a hold of one of these things, the slower it goes, the less force you feel. But the jam it, then it has more force reaction. It's a way of dissipating energy out of the system, right? So there's going to be some cases where we're going to be dealing with drag and air resistance, and in those cases, it's going to be a function of velocity. Okay. How about function of position? When would accelerations be a function of position?
Anything where you're like pulling back a spring or something.
Yes, springs. Right? Springs will do that, right? The more you push on a spring, the more force it pushes back. The more force there is, the more acceleration there is, right? And so those will absolutely be part of it. We'll also say real gravity. What's another force that's dependent on position? Not very many forces out there.
Magnetic.
Magnetic. Yep.
Would the electric field fit into that as well?
Same thing, yeah, kind of tied to the electrical field and stuff, or magnetic fields. Ugh, those are weird, aren't they? Magnets and gravity. Like those are like we're like, oh, they're there. They're forces. They exist, right? But then like, don't know how they work, right? I don't know how they work. I know that they travel at the speed of light, which is weird, right? There's some more deep thoughts for you guys on a Friday, right? The gravity travels. So like, if the sun was snatched away and just disappeared right now, right? We would just be sitting here for 8 minutes, and then 8 minutes from now, right? Then we'd take off on a tangent. Like, again, if you believe in these sorts of things. That's the common theme. I'm gonna say that a lot in this class. Okay. We got 5 minutes. All right. Okay. So then, how do we do? Do I get at this? How do we do these again? So I think I would be pretty safe to say that you dealt with these two in your physics. These other two, how we solve them, get a little bit different, right? You're going to want to solve them the same way, but you can't. Okay, and we'll dive into these things. Okay, so if we have acceleration as a function of time, right? Oh, I guess before we do that, probably more importantly, let's just kind of set a framework over here, right? On how we're going to solve these. I kind of added this note later on. So just, again, me trying to lay out how you're going to see these problems, or like some sort of strategy for solving these problems. So we have different ways these problems are presented. Make a big note here somewhere. Right? One way is they're going to give us acceleration. Right? And that's actually that's how we're going to start out doing these problems, is they're going to give us the acceleration. Here's an acceleration equation, okay? Later on, right? Later, we derive this, right? And what I mean by that is later on, we're actually going to do a free body diagram where then some of those forces are going to equal the mass times acceleration. You take those forces, you divide by mass, and there's your acceleration equation. That's what we're building up to. But right away, they're just going to give us this acceleration equation. Okay, and then we move to velocity and then position. So I'll put a 1 on there. 1, they're going to do that. They're going to give us acceleration, or later on we're going to derive it. And then from that acceleration, they ask us something about the velocity, or ask us something about the position, right? So we have to go from acceleration to velocity to position. And that'll be done via integration, right? That's it. So we have, right, because they're the derivative stuff. We're going the opposite direction, so we're going to have to integrate to go that direction, right? Right, so they're going to say integrate, right? The other way that they can present these things, too, is they're going to give us position equation or velocity equation, and we have to move to velocity, then acceleration, right? If applicable, depending on if they give a position, you'd have to go through both of those. Right? I think that over the years, that little added thing, because again, trying to picture what we're doing, that's what it is. So they're going to get two different ways. They're going to give us the acceleration. We have to find the acceleration. We're going to go velocity and position. Or they're going to give, hey, here's this position equation. Tell me what the velocity is, and tell me what the acceleration is. And this would be taking derivatives. This last one. Okay. The stuff down below that I talk about, that we're going to dive into down here. This stuff down here, we're going to say, okay, well, say I give you an acceleration equation. How do you go to velocity and position? That's more difficult. Going from position to velocity to acceleration. That's easy, right? That's to take a derivatives of things. Going the other direction is where things get a little more complicated. And so that's what we're going to do. Next class, I'm going to go through how do you do accelerations a function of time? How do we use constant accelerations, which is it's a constant, it is accelerations a function of time. It's just they don't change with time. So it's just a subset of the first one. Then we'll talk about how do we do accelerations a function of velocity, and then accelerations a function of position. And you'll see we have to use this chain rule and things get a little crazy. And then we'll start doing some examples, right? So your homework that's due next Friday is related to these types of problems. You probably won't have enough stuff until Monday or Wednesday to do the assignment because we haven't got through far enough stuff yet. So cool. Break.